All right, number 11 is look at our problem. It tells us we've got a certain number of grams of water, and it's asking how many grams of oxygen. So this is a gram-gram question. Three steps. So we're going to start with grams of water, and we need to change that into several things here. Ultimately, we need to end up with grams of oxygen. So I'm going to start with grams of water. Cancel that out, turn it into moles of water. I'm going to cancel that out and turn it into uh, moles of oxygen. Then I'm going to cancel that out and turn it into grams of oxygen. Change colors, so I can put the numbers in here. So 83.49 at the beginning. Right. Molar mass of water. So 1 mole of water is 18.02 grams. Molar ratio between oxygen and water, getting that from the formula. So there's a 1 in front of the oxygen, there's a 2 in front of the water. And then the molar mass of oxygen. Since we've got O2, we have to double oxygen on the periodic table to get us to 32. Once we got that set up, start with that in the calculator, divide by 18.02 since it's on the bottom, divide by 2 since it's on the bottom, multiply by 32 since it's on the top, and that should get us an answer around 74.13. So again, that's a gram-gram question. Got to go grams, moles, moles, grams to get that. Question 12 and 13 are about limiting and excess reactants. Again, a limiting reactant simply is it's what we're going to run out of in a chemical reaction. So if we've got a couple of things that are reacting together, limiting means we're going to run out of it. It's going to be gone. So once we kind of get to the end, the limiting reactant is what causes the arrow to kind of stop working. The process of whatever reaction we have is going to end at that case. So in number 12, I gave an example that if we use oxygen and hydrogen to make water, at the end of the reaction, if there is hydrogen still left over, it means we still have some hydrogen, but the oxygen is gone. So since the oxygen is gone at that point, then oxygen is our limiting reactant. If the question asks about the excess reactant, the excess would be hydrogen. Water is not going to be an answer at all because water is a product. Any of these questions that ask about a limiting reactant or an excess reactant, it has to be about the reactant. So in this case, it's oxygen and hydrogen reacting together. Now, we can quantify these things a little bit as well and start looking at numbers. So on question number 13, it says if we had an equal number of moles of hydrogen and oxygen, which one would be the excess? Which one would we run out of? So in this case, the recipe or the balanced equation is I need 2 hydrogens basically for every oxygen. So if we had equal number of moles of each, in other words, we could just pretend, right? We could come up with whatever number we wanted to. What if we had 2 moles of each? Well, if I had 2 moles of each, think about what would happen here. If I had 2 moles of each, then I would use 2 moles of hydrogen to react with only 1 mole of oxygen, and then I would have 1 mole of oxygen left over. Because again, I need twice as much hydrogen as I do with oxygen. So if we had equal numbers, I'm going to run out of the hydrogen first because I don't need as much oxygen, all things being equal. So we can use the balanced equation kind of as our recipe. Again, it's kind of like saying if I had 2 pieces of bread and 1 slice of cheese for every sandwich, well, what if I had 10 slices of bread and I had 10 slices of cheese? What am I going to run out of first making my sandwiches? Well, I'm going to run out of bread first because it's going to take me 2 slices of bread to make a sandwich. So these 10 slices of bread would allow me to make 5 sandwiches. The 10 slices of cheese would allow me to make 10 sandwiches, but I'm going to have already run out of bread by the time I get to the 6 piece of cheese. So again, bread is my limiting reactant. What am I going to be left over with? In my bread and cheese example, the cheese is what I'm going to be what would be left over. In the example up here, I'm going to have oxygen left over because I'm going to have run out of the hydrogen. So again, we can use the numbers in our balanced equation to kind of determine what would we run out of first if we're given different amounts of these things. All right, moving down to 14, back to some math. 14 and 15 are just molarity questions we can remember, hopefully, and it's on the back of the sheet we have with our periodic table. The molarity is moles over liters. So number 14, all that we need to do is put 20 over 600. So 20 over 600 is going to give us, I believe, 0.03. And that should be, if it finds molarity, that should be with a capital M. That's all we need to do for that. Remember, again, molarity is a measure of concentration. It's how many moles are in the solute. How many moles are in the solvent. So how many moles of solute are basically in the solution, or in this case, it's the solvent, because this is going to be liters of solution. So it's just a ratio that we're getting here. So the higher this number is, the more molarity we have. Generally, the stronger or more concentrated the solution is. 15, same kind of question, but we're kind of rearranging it because number 15 is asking about the volume. Well, again, it's moles over capital M, capital L. So if I'm solving for capital L, then it's moles over capital M. In this case, so I've got 1.15 on the bottom, and I've got 0.75 on the top. Put those in together with the calculator, and we should get 0.65. And this should be in liters since it's asking for volume. All right, 16. Solubility curves. We're asking if it's saturated, unsaturated, or supersaturated. The lines on these graphs are the saturation points. So the line that we graph is the maximum amount that can be dissolved at a given temperature. Temperature is the x-axis. It increases from left to right. The grams of solute, that's the y-axis. It increases as we go up. Most of these lines have a positive slope, which means that as the temperature goes up, we should be able to dissolve more. There's an exception here with NH3, which dissolves worse as it gets warmer. In describing what's going on in the question, is if I dissolve 70 grams at 60 degrees, that means if I start here at 60 and I scroll up here to about 70, if I put a dot where the arrow is and compare that to the KNO3 line. So if I put a dot where the arrow is and compare that to the KNO3 line, the KNO3 line, again, the line is the saturation point. And if you look at this dot, I still have some room that I could add a little bit more. The idea is as I add more and more solute to the solution, my dot would move higher and higher, going vertically up on the graph. If I stop short of the line, that means that I've still got a little bit of extra stuff that I can be able to add to it. So since this dot is beneath the line, this is going to be an unsaturated solution. If we graph a dot on the line, that's going to be a saturated solution because that's the most that could dissolve at that given temperature. And in rare occasions, it's possible to graph something above the line, assuming that we had first heated it up in order to dissolve it and then let it cool back down. So if the dot is above the line, that's when we're going to be super saturated. So just in brief, if we're comparing again the KNO3, if it was on the line, saturated. If it's beneath the line, unsaturated. If it were above the line, it's going to be super saturated. Look at the next item, 17. What's the greatest amount of KNO3? In other words, that's just asking us what's the most I could dissolve in there. In other words, saturating it. 60 degrees, and I couldn't dissolve anymore. So if I start at 60 degrees and start working my way up the graph to KNO3, I'm going to start here at 60. I'm going to go up to the graph to hit KNO3. Once I see that amount, I can then move to the left, ask myself, how much is this amount? It's roughly 90. It's a little bit less, probably 88, 89, 90. But that dot corresponds to this amount and this temperature, putting both of those two things together. So the dot is always tying two pieces of data together. It's always tying the temperature with the grams of solute together. So 88, 90, somewhere in there will be our proper answer. All right, so just words, no math at this point. Which will cause a solid to dissolve faster in a solution. So this is about the rate of doing it. Generally, if we heat it up, it's going to dissolve a little bit faster. Generally, if we stir it, it's going to dissolve faster. And generally, if we crush it up to make it into smaller particles, it's going to dissolve faster because of the amount of surface area that we have. Cooling it's not going to help us solid. It's going to make it worse. Bigger glass is kind of irrelevant. How fast it dissolves should be independent of what we put it in. Moving down the last two, which would dissolve through dissociation. This word dissociation should get you to think of an ionic compound. Ionic compounds are metals and nonmetals, positives and negatives. Dissociation means that they're going to kind of pull apart from one another due to some other forces. So if something is going to dissociate, then it is something that's ionic. And if it's something that's ionic, then it's going to be something that is a metal and a non-metal combination. So if we go through the list on number 19 about which ones would dissociate, sodium chloride is ionic, water is not, carbon dioxide is not. KBr, because K is a metal. NO, I don't have any metals there. CO, no metals there. Magnesium oxide, metal there. So these three things would dissociate because they are all ionic. I know that they are all ionic because I have a combination of a metal and a non-metal. And finally, number 20, when water or any solvent surrounds the solute to dissolve it, the mixture is undergoing what process? Use these first four letters to help you remember that. So what a solvent does is use those first four letters, SOLV. The process is called solvation. When we see this term, this can happen with covalent or ionic substances because this is actually referring to the water or the solvent and not to the substance that is being dissolved. So water basically acts similar to one another no matter what it's doing with that.